Whenever I talk to a graduate student, an undergraduate student, a professor, or acquaintance at a cafe, I always ask, your problem? Does it have a symmetry? It does. Well, you must use it. So that's what we'll do now. Suppose on our lattice we have a Hamiltonian. Hamiltonian typically looks, the simplest version is something that's bilinear in a field. So that has a term, for example, a mass square term, or springiness of a harmonic oscillator. And then has a term that says, if there's lots of curvature, I should be punished for it. I would like things to be smooth. And as I just showed, the curvature is measured by Laplacian. In harmonic equation, if it's harmonic equation, has to balance them. Now, because this is something square, by symmetry, there should be 1/2 in front of it. And we call it something. For example, we call it Hamiltonian or action or Lagrangian or whatever. This is one level of abstraction from your particular quantum mechanics or elastodynamics class. This depends on a field. This means that we are summing over the whole. This is a lattice state, all the components on a lattice. This is its transpose. And we do an operation on it. We multiply it by 1, and then we measure its curvature. And what happens if I do a lattice translation? If I do a lattice translation, so I change, what I call 0, 1, 2, 3 on my rotational clockwork that I showed before, then what will happen to this term, it'll be shifted by my lattice. There'll be a transpose. This guy will get shifted by my lattice. This is just a matrix. Nothing happens to the matrix. And there's 1/2 here. And now we have a new action which is measured on a lattice state which is translated. Now in general, that should be something different. However, we have a symmetry. Notice this Laplacian operation was defined in terms of lattice shift and inverse lattice shift. That means that if I compare sigma and apply it on the operator in 2 orders, so I compute a commutator, this is just function of sigma, so it obviously commutes, so commutator is 0. That means that our operator, this matrix that measures, let's say, energy of a state, is translationally invariant because sigma is generating translation. I write this as transpose, so this is ft. That is sigma -1, that's a transpose of the translation operator. The matrix is what it always used to be. Then this guy, I stick in a matrix and I just have my state. But because this commutes, sigma just goes through the whole so-called inverse propagator or harmonic action or whatever you want to call it. And it cancels out. So I find out that action or Hamiltonian or energy or whatever computed on a shifted state is the same as computed originally. In other words, action is invariant under translation. Our law of motion doesn't care which side we call 0, 1, 2, 3, 4. So we have a symmetry, so we must use it.